welcome to Intro to Vectors lesson. Today we're going to start talking about motion in 2 dimensions, which means it's moving in 2 directions at once. That could be up and over, or up and out, or over and out, any of those. Most of the time we're going to be looking at motion that is up and down in the y direction, and also over, side to side, in the x direction. In order to be able to analyze motion in 2 dimensions, we need to know a little bit about vectors and scalars. And we've already kind of talked about these. But a little review is that a vector is something that has magnitude as well as direction. So some vector quantities are displacement, velocity, force, and momentum. So we know the direction of velocity when we are solving a problem because we usually indicate if it is positive or negative. And that is telling us which direction it is traveling in. Another example of direction is north, south, east, or west. Or another example is left or right. Anytime any of these 3 things are indicated, you have a vector quantity. So you not only have the number, you also know the direction. On the other hand, a scalar only has magnitude. So some scalar quantities are mass, time, temperature, speed, and distance. So we cannot ever have a negative speed. If I were to tell you my speed in a car, I would say 90 kilometers per hour. But you don't know if I'm traveling north, south, east, west, up, down, over. You have no idea. All you know is how fast I'm going. If I indicate that I'm going 90 kilometers per hour east, that is the velocity of my vehicle. So vectors have magnitude and direction, and scalars only have magnitude. We usually, in math and science, represent a vector by an arrow. And in mathematics, this is called a ray. So this right here is our ray. It is our vector. The length of this vector represents the magnitude. The longer the arrow, the larger the magnitude. And the direction of the vector represents the direction. So if I have a vector that is doing this, let's say these vectors represent velocity, this means I have a negative velocity and I'm going very fast. But if I have a vector that's like this, that means I'm moving in the positive direction, but my velocity is very, very low. I'm barely moving. I'm moving very slowly. We can add vectors together. Just like we can add velocities together, we can add vectors. It's the same thing. So for vectors in 1 dimension, meaning they're all going the same direction, right and left or up and down, we can just add or subtract them. That's all we need to do. All you have to do is be careful of the signs. So here are 2 examples on these graphs. The first example is one vector that is 8 kilometers. So this is the displacement. It's 8 kilometers to the east. And the next vector is 6 kilometers to the east. So if I move 8 kilometers to the east and then stop, and then move another 6 kilometers to the east, my total displacement is 14 kilometers to the east. I add 8 plus 16, and it gives me 14. The second example down here is what would happen if I walked away 8 kilometers to the east, but then I turned around and walked back 6 kilometers to the west. My overall displacement in this case would only be 2 kilometers because I move 8 kilometers to the east, which I'm going to call positive, but then I move 6 kilometers in the other direction, west, which I call negative. So I have to subtract these 2 from each other, and my total displacement is 2 kilometers. So when you're adding vectors, you always have to be careful of not only the magnitude, but what direction the vector is pointing in. So the addition of 2 or more vectors is called a resultant. So, if I have vector A here, and I want to add vector B, what is my resultant? Well, this is how you would do it. You take A, and you lay it down, and you add B, where you put the tail of B to the tip of A. When we add vectors, we call it adding tip to tail. So we have the tip of A connected to the tail of B here, and the resultant, or R, is from the tail of A all the way to the tip of B. It does not go from the tip of B to the tail of A. It goes from the tail of what you start with to the tip of what you end with. So now, if we want to do B plus A instead of A plus B, we have to take the tail of A and add it to the tip of B. So it looks like this. We have B up and down here, and we add the tail of A to the tip of B, and our resultant, R, is from the tail of what we start with to the tip of what we end with. So the tail of B to the tip of A. And then A minus B. Well, if we have minus B, that's the same as saying negative B. So if this is our B right up here, if we want negative B, it's going to be the same length, because we're not changing the magnitude, but it's going to be pointing down. So this is negative B. We have changed its direction, but not its magnitude. So now, in order to add A plus negative B, which is the same as A minus B, we have to take the tail of B and add it to the tip of A. So we have the tail of B, negative B here, and we've added to the tip of A, and our resultant vector goes from the tail of A to the tip of B, the tail of what we start with to the tip of what we end with. If the motion is in two dimensions, let's say left and right and up and down, or east and west and north and south, the situation is a little more complicated. So the actual travel paths are right angles to another. We can see that here. If we first move 10 kilometers to the east, and then we make a left-hand turn and move, 5 kilometers to the north, this right here is a right angle, 90 degrees. And hopefully all of you know when you have a triangle with 90 degrees in it, you can use the Pythagorean theorem to solve for your hypotenuse, or this guy right here. So if you're adding two vectors that are at right angles to one another, you use the Pythagorean theorem. So your resultant vector, r squared, which in math class would be c squared, is equal to a squared, which we'll say is the 10 kilometers east, plus b squared, which is the 5 kilometers to the north. So to solve for this, you have to take the square root of both sides. So that would be r is equal to the square root of 10 squared plus 5 squared. And if I take out my calculator here, 10 squared is 100 plus 25, which is 5 squared. And you take the square root of 125, and our resultant vector is equal to 11.2 what? We always need units. So our resultant vector here is 11.2 kilometers. And we know that because both our x and y coordinates are labeled with kilometers, but which direction does it travel? Well, in order to figure out direction, just look at your resultant vector. Here it's going up and over to the right. So it is going northeast. It moves a little bit north and a little bit east. So the entire answer here for your resultant would be 11.2 kilometers to the northeast. If you left off the northeast part, that's like leaving off units. And we wouldn't know what direction you had traveled in. Therefore, your resultant wouldn't actually be a vector quantity, it would be a scalar, which is wrong. So always remember to indicate the direction by either putting a coordinate like north, south, east, or west, by labeling it left or right, or most likely by labeling it positive or negative. And just a heads up, it turns out if we add these vectors in the opposite order, so instead of adding x plus y, we add y plus x, we get the same exact result. Whoop. So we can see that here. If we add 5 squared plus 10 squared equals r squared, we do the same steps. We have 5 squared plus 10 squared equals r, and in order to have that, we need to take the square root of both sides. And when you do this calculation, it still comes out to be 2? Yep. 11.2 kilometers. And again, to figure out what direction your resultant vector is in, look at the direction. We have added tip to tail. So we have the tail of our x-axis coordinate to the tip of our y-axis, and it is still going a little bit north and a little bit east. So it's still 11.2 kilometers northeast. So it does not matter in which order you add vectors. It will always give you the same result. Just make sure you watch for signs. And it turns out we can add vectors even if they're not at right angles. And we do this using the tip to tail method. So let's walk through this one. We have V1, which looks like this, and we're adding V2. And V2 is straight down. So I want to put the tail of V2 to the tip of V1, just like that. And the third one is V3, which is just straight over. And I want to put the tail of V3 onto the tip of V2. And now I can draw my resultant vector. And remember, the resultant goes from the tail of where you started to the tip of where you end. So your resultant looks just like that. That's the same thing they got here. This is a little more complicated, and we won't end up doing it too much, but it's good to know how to add vectors tip to tail, even when they're not at right angles to each other. There is, on top of the tip to tail method, there's the parallelogram method, which definitely is not my favorite, but it's possible. You can do it this way. So the tip to tail method, if we were to add V1 plus V2, is we draw V1, and then the tail of V2 goes to the tip of V1, and our resultant is from the tail of where we start to the tip of where we end, and it looks like this. The parallelogram method is where we lay them out tail to tail. So V1 looks like that, and then we put the tail of V2 to the tail of V1. But the resultant here does not go from the tail of where we started to the tip of where we ended. It is, if you were to draw where these connect, that is your resultant. Like I said, this is not the way that I prefer to do it, but if this way makes more sense to you, then all the more power to you. So like the example we did several slides ago, in order to subtract vectors, we have to define the negative of a vector, which always has the same magnitude but points in the opposite direction. So if this is V right here, minus V is exactly the same length, but in the opposite direction. You can almost think of it as chopping the head off over here and putting it down on the bottom. And now it becomes the negative of what it was. We add the same way that we add positive vectors together, tip to tail. It's just that now you have a negative vector, it has reverse direction. So if we are taking V2 and subtracting V1, we have V2 that goes up like this, and we want to subtract v1, which means we want to turn v1 into the negative. So we take the head, chop it off, and put it over here on the end. And v1 ends up looking like that. Same magnitude, same length, but the opposite direction. And now we can do tip to tail, where we go the tail of where we started to the tip of where we end for our resultant. It's the same thing they get right over here. We can also multiply vectors. So we can not only flip them around if we're making them negative, we can also change their magnitude. A vector v can be multiplied by a scalar c, and the result is the same direction but a magnitude of c times v. So for example, if we have the vector v here, if we want 1.5v, we have to keep the arrow pointing in the same direction because the direction hasn't changed, but its length has increased by 1.5. If we want to have negative 2v, the negative tells us that it flips direction. So we took the head off from here and we moved it down here. So now it's pointing in the opposite direction. But it's also going to be twice as long because it's 2 times v. So we just learned a lot about vectors. And this is just a brief summary, a recap of what we learned. We learned that you can add tip to tail. We learned that a negative vector is the same as the positive one, so it has the same magnitude, but it's opposite in direction. We learned that when we multiply by a scalar, or a number that does not have direction, the magnitude changes, but the direction doesn't. So if we have v and we want 2v, we just make that arrow twice as long. It does not change direction. But if we were to multiply by negative 2 to get negative 2v, it's twice as long and it points in the opposite direction. And finally, when we add perpendicular vectors, we have to use the Pythagorean theorem. A squared plus b squared equals c squared. So this is a long video with a lot of stuff in it, so now would be a really good time for you to take a break and come back so that your brain doesn't melt out of your ears. Okay, so I hope you enjoyed that break as much as I did. I really needed a drink of water there. And now we are going to push ahead and do a few more examples of adding vectors. So here are some useful links so you can actually see vectors being added in real time. So we have vector A here and vector B, and we want to add them together. So we do tip to tail. We take A, and we add the tail of B to the tip of A, and we get our resultant C. So let's watch that again. And remember, you can always do it the other direction too. No matter which order you add A and B in, it always gives you the same result. So if we watch this again, we have A, add tip to tail with B, and then draw a resultant from the tail of A to the tip of B. You can add them in reverse order, and you will get the same result. Both C resultant vectors are the same here. Remember, when you subtract two vectors, it's the same as adding, except you have to make one of them negative, which means whichever one you're subtracting needs to be pointing in the opposite direction. So if we have A and B here, we have A, and we want to subtract B, so we make B negative B, flip it around. If we add more than two vectors, we add tip to tail. So we have A, B, and C here. And we have A, we add tip to tail with B, and we get A plus B, and then we add tip to tail with C. And the resultant is this blue line, from the tail of where we started, the tail of A, to the tip of where we end, which is the tip of C. And finally, if we are adding vectors by components, which means we're breaking the vectors down into their x and their y, it looks like this. We have A, and we have B, and we add them tip to tail, and you can see, you add the x components of both A and B, and you add the y components of both A and B, and you get your resultant, which is the sum of those. So overall, your C has an x component of 12, and that's because A had an x component of 7, and you add the x component of B, which is 5, and 7 plus 5 is 12. And the same with the y. So adding vectors by components is really very important, and we will be breaking things down into components quite a bit. So any vector can be expressed as the sum of two other vectors, which are called its components. Usually the other vectors are chosen so that they are perpendicular to each other. Your components do not need to be perpendicular to each other. However, when you do make them perpendicular, it makes your life a lot easier. So if we have our vector here, vector v, we can look at how much of this vector is x, and we can also look at how much of this vector is y. We make an imaginary line. So let's say we're shining an imaginary flashlight on our vector. The shadow we will get from this flashlight is our y component. And if we take this flashlight and we move it so that we're shining it on the other part, we're shining from the top down, the shadow this will make is its x component. So you can see that over in this diagram here. The x component is right here, and the y component is right here. So we have broken it down into x and y, and we have a little bit of experience with this when we talked about forces. So this is just making clearer what we did when we talked about forces on an inclined plane. When the components are perpendicular, it makes your life a lot easier because you can use trigonometric functions. That means you can use all of these things. So remember, in math class, you probably learned this little ditty called SOHCAHTOA. SOHCAHTOA. So that means the sine of any angle is the opposite over the hypotenuse. The cosine of any angle is adjacent over hypotenuse. And the tangent of any angle is the opposite over adjacent. So tangent of this angle is opposite over adjacent. The cosine of this angle is adjacent, this one, over hypotenuse. And the sine of this angle is the opposite over the hypotenuse. Another really nice thing about this, keeping your coordinates perpendicular to each other, is that you can use the Pythagorean theorem, which always comes in handy. So if you can, always make your component vectors perpendicular to each other. It just makes it so much easier in the long run. When you add components, you can just add them arithmetically, which means you can just add them together. So if we have vector 1 and we add tip to tail vector 2, we get the resultant, which looks like this. These aren't at right angles to each other, so it's going to be really hard to figure out what v, or our resultant, is. We can't use the Pythagorean theorem here. So what you can do is break each of these down into their x and y components. So this is the x component of v1, and this is the y component of v1. And we are going to add that to the x component of v2 and the y component of v2. So you literally take this and add it to this. So you end up getting this, which you can see right up here. For the y, you take this and you add it to this, which gives you this, which you can see over here. And now, the y component of your resultant and the x component of your resultant are at a right angle to each other, and you can now solve for this. So this is a really messy diagram, I understand, but hopefully it makes sense to you. Adding vectors by components is super important and one of the easiest ways to add them. So make sure you understand this. If you do not understand this, please come see me for extra help or see Mr. Munson for extra help, and we would gladly walk through examples with you. So to summarize, whenever you're adding vectors, draw a diagram. You always want to look and see what your vectors are going to look like when you add them together. And when you draw a diagram, remember, tip to tail, always. Tip to tail. Once you've drawn your diagram, choose your x and y axes. Normally, x and y axes look like this, with this one being your y and this one being your x. However, remember from when we analyzed forces on inclined planes, this doesn't have to be true. So if there is a more convenient x and y axis, you can use that as long as you keep x and y perpendicular to each other. After you've chosen your axes and you have your picture, resolve the vector into x and y. So break them down. Remember the little flashlight trick. If you were to shine the flashlight from the side, what is the shadow it would cast on the y-axis and what is the shadow it would cast on the x-axis? Those are your components. After you have your components, you can calculate them using sines and cosines. So you may have a picture like this, where you have your x component and your y component here, and if you know your angle, you can calculate your x and y components using sine, cosine, tangent, and the Pythagorean theorem. Once you know how big your components are and in what direction they are pointing, you can add them together. So add all of your x's together and all of your y's together, and make sure if they're pointing in opposite directions, you make the proper arrows negative. And finally, to find the length and direction of the vector, use the Pythagorean theorem. Or, if you're not trying to find the hypotenuse, you're trying to find one of the sides, you can use the tangent of the angle. So your homework for tomorrow is to answer the following questions and get just a little bit more practice with vectors. So 1, what is a vector? What is a scalar? And give an example of each. And 2, a car travels at a speed of 55 miles per hour north, then turns and travels at 40 miles per hour west. What was his overall average velocity? So remember, draw a picture and add it graphically so that you have a good idea of what's going on, and then you can choose a method from there. Have these done for the next time you come into class.